Hello class and welcome to week 9 lessons. I'm sure you're all pretty excited because we are getting into some nice electronics material, and I know that's really what excites you the most about studying in this college. You've come to learn electronics and telecommunications. So week 9 we begin with the first serious semiconductor device, electronic device. And although in the textbook Sedra and Smith, um, after we completed chapter 3 and 4, which was semiconductors and then diodes, chapter 5 talks about a certain type of device, MOSFET, transistor, and then chapter 6 talks about BJTs. What I've done is shift the order so that we cover chapter 6 first, BJTs, and then we will do chapter 5 in the next week. So instead of doing chapters 5 and 6, I'm doing chapters 6 and 5 by reversing the order. The textbook says you can do it, in either order. They don't really mind, and I feel after covering the previous material, the BJTs is a easier step forward than bringing the other chapter first. So anyway, we will do both. I just want to start with BJTs chapter 6 first. Okay. Alright, so I'm on slide 1, which is just the title slide of my PowerPoint. I will try and do the lecture material in this recording. It's totally lecture, so all 50 minutes you're just going to learn the theory material, and then I will have a full 50 minutes for problems. But that only covers half the chapter. Then in the next 2 recordings I'll cover the remainder of the chapter. Okay, so moving on to slide 2 is where you can see all the sections in this particular chapter. So we have a total of 9 sections, but luckily for you, or unluckily depending on how eager you are to learn all this material, in this class EE 280, I only have to do the first 5. The remaining 6, 7, 8, 9 in this chapter and the next chapter also, which is chapter 5, they're in the same order. 6, 7, 8, 9 will be covered not by us in this class, but by your next professor in your next class, EE 380. In fact, EE 380 will likely begin with this topic on BJTs, section number 6. So basically we have to cover in this class the first 5, and so I will do that in 2 halves. The first half I will do 1, 2, 3, and then 4, 5 in the next half or the next recording. Okay, so we have to cover device structure and physical operation, current voltage characteristics, and BJT circuits at DC in this recording, just the theory. And on these same topics we have a whole bunch of problems that I'll cover in the next recording, and then 4 and 5 I'll wait for the later recordings. Okay, so let me move on to slide 3. Now again I want to caution you that there is just too much material in every chapter in this textbook. Sedra and Smith, I feel, compared to the previous circuits book, Nielsen and Riedel, there is much more material in each chapter, each section in Sedra and Smith, and so it's much harder for a professor to cover everything. So my job is to try and summarize the main points and the main formulas, so that I feel that I've given you a good overall understanding of the important points, but you should expect to spend a lot of time reading the textbook by yourself so that you pick up on many of the smaller but also essential items of information. Again, from an exam perspective, doing tests and quizzes, I will cover everything that's required. But if you really want to learn all the details of the material, there's plenty of material in the textbook, and depending on your time and your interest, feel free to spend many more hours on the text material. Okay. Alright, so we got 6.1.1, 2, 3, 4, 5 all under 6.1. So let me get started. I'm on slide 4 now. The simplified device structure and modes of operation. So we are talking about the bipolar junction transistor, BJT, right? And bipolar really means that the flow of current happens both with electrons and with holes. So negatively charged and positively charged current carriers. Okay, that's why it goes by the name BJT, bipolar junction transistor. So these block diagrams, or these high-level diagrams that I'm looking at on page 4, they give you the basic structure of a BJT transistor. So there are 3 regions, and this is all built around silicon mostly, or germanium. Most commonly used material is silicon. So we have I hope you remember what we studied in the last 2 chapters, chapter 3 and 4, semiconductors and diodes. And remember, we spent a lot of time on the PN junction. So what you'll notice from these 2 drawings, on the left we have 2 junctions, right? 2 PN junctions. There's a NP junction and then there's a PN junction, right? Similarly, on the drawing on the right side, we have again 2 junctions, a PN junction and an NP. The leftmost region in the silicon block is doped as N-type. Then the middle section is doped P-type, and then again N-type. And on the left side, that's called an NPN. And on the right side, we have PN and P, which is the opposite. So there are 2 types of BJT transistors. One of them is called the NPN type and the other is called the PNP type. Okay. So in the diode, we had an anode and a cathode, right? The anode was positively doped. It was a P-type semiconductor, and the cathode was negatively doped. It had a N-type flavor. So here you notice that we have different names. We have 3 terminals. One of them is called the emitter, one of them is called the base, and one of them is called the collector. And the emitter is shown with an E, base with a B, and a collector with a C. This may have disappeared, but you can see it on this side, PNP. So whether it's NPN or PNP type BJT, you're going to have an N-type emitter. You'll have an emitter, a base, and a collector. Now whether the emitter is an N-type or a P-type depends on whether it's a NPN or PNP transistor. Okay. Also, we have electrodes that are attached, which are metal connections to bring the N-type out via a terminal on the transistor. So you do that for the 3 regions, emitter, base, and collector. Okay. If I move this to the oh, there you go. You can see it now. Okay. So that is your first introduction to emitter, base, and collector, and the PNP and NPN semiconductor structure. Okay, I'm going to move on to slide 5 now, and here I went back a little bit because I wanted to emphasize one point, and then we'll continue. And this point is that, and this comes from the PN junction behavior. If you have a PN junction like this and it is reverse biased, right? That means you have the negative terminal of the battery VR connected to the P area and the positive terminal connected to the N area, so it's reverse biased. Then the electric field has become much stronger because of the reverse bias, right? You know that. Now if you put an electron here into the P side, this electron is a minority carrier in the P side, right? It is supplied, it's injected into the this region, the P region. Now what happens is the electric field in the depletion region, you know the depletion region and you know E, it's attracting the electron towards the positively side holes on the N side, right? So the electron is put here, but it's being attracted towards this side. So the electron, boom, it moves swiftly towards the N side, and we call that motion, the electron is swept into the N region. So we can also say that the reverse bias PN junction can efficiently collect the injected electrons, okay? So the injected electrons are collected and moved into the N-type region by having this reverse bias. So this is a fundamental behavior that becomes important as you start to understand the operation of the transistor, the three-terminal device called the transistor, okay? So I move to slide 6, and here is a little more detailed analysis of the transistor, and I'm on slide 6. Okay, so what you notice is a bunch of currents, voltages have all been attached, right? 2 slides ago we showed you the block of an NPN transistor. On slide 4 we just named the regions emitter, base, collector, N-type, P-type, N-type, or the opposite here on the right side. But now we are going to mostly study NPN, because PNP, almost everything reflects the same logic, but it's reversed with the polarities being reversed. But otherwise the behavior is the same. So let's focus, prepare to focus a lot on the NPN transistor. Okay, so also we introduce a term active mode. So for the moment ignore that, you'll learn very quickly what an active mode is. But for now just look at this drawing and let's focus on some of the important elements here. First of all, this is an NPN transistor, so this is N region with a lot of electrons, P region with a lot of holes, and again an N region with a lot of electrons. Now there are two batteries connected to these three junctions, right? One junction is kind of common, it's the base, and so the first battery called VBE, capital BE, the positive of this is connected to the base and the negative is connected to the emitter, right? This is the N region, the emitter. Now because the positive is connected to the P region, which is positive, and the emitter is connected to the negative of the battery, which is the electron, the negative region, we say that this junction, the electron base junction, remember there's two PN junctions here, right? So the first junction is the EBJ or electron base junction, and the other junction is the BCJ, which is the base collector junction. So this junction is positively biased, right? Because the N region connects to the negative and the P region connects to the positive of the power supply, it's forward biased. Here you notice that we have done the opposite. We have reverse biased the other junction. So the collector region is connected, which is the N region, right? So the N region you normally want it to connect to a negative of the battery, right? But we have done the opposite. we've taken the N region and connected it to the positive of the battery, and we have taken the P region, which is positive, right? Generally speaking, it has excess of positive holes. It is connected to the negative terminal of the battery. So this is important to understand. For normal operation or active mode of a transistor, the first junction, the emitter base junction, is forward biased, while the second junction, the base collector junction, this junction, is reverse biased. Okay. So a couple other things to remember. In an NPN transistor, electrons go from the emitter to the collector, okay, from here to here. Thus, the conventional direction of the current is from the collector to the emitter. Because remember, we have two types of directions of current, right? Generally, when we say direction is positive, we mean positive battery into the circuit and then coming out into the, going into the negative, right? But that we know is the exact opposite of how electrons travel. They travel from the negative terminal of the battery. So that's what this note is saying. Now, why do we say electrons travel from the emitter to the collector? As shown by this big block arrow, injected electrons from the emitter travel like this to the collector, and that is the main source of current inside the NPN transistor. So there's a lot of electrons in the N region because it's heavily doped with electrons, and those electrons, they go into the base and then travel on to the collector. That's the basic structure, movement of charge inside an NPN. Now you'll notice that not all the electrons from N go into P. Part of it actually stays within the P, and the remaining electrons go into the N region, which is the collector region. Okay, so this large arrow is IE, or the electron current, and this somewhat smaller arrow is the collector current. So IE, IC, and then a much smaller portion is IB. But IB consists of two components, IB2 and IB1. IB2 is injected holes from P region going back into the N region, and then recombined electrons. That means the electrons combine with the holes here and kind of just disappear in the P region. That is another component of base current. So base current has two components, IB1, IB2. Electron current has only one component, IE or big IE or I big E, and collector current only also has one component, which is just IC. Okay, so injected electrons, collected electrons, diffusing electrons, which consists of both of recombined electrons and injected holes moving in this direction. Okay, so all these currents, which are basically movements mostly of electrons but some holes in an NPN. In a PNP it's kind of reversed. You have most of the current happening because of hole movement, but in an NPN transistor most of the current is because of electron movement. Okay, so remember, this is fundamental. You have to understand this, spend some time understanding this, and because electrons move here, we show the current direction with these arrows outside, because this is conventional current direction. Okay, and so we have an IE in this circuit and an IC in this circuit. Okay, and then an IB in this circuit. Now there's capital VBE and small VBE. Okay, they are two different. Mostly they are almost the same in most cases, but there's a slight difference. Remember, this is a battery voltage while this is the actual voltage across the semiconductor junction, the PN junction. So when you apply a forward bias, we know that there is like a cut-in voltage for a semiconductor junction to begin to conduct, right? And so this VBE is more about the actual voltage across the junction itself, while the external voltage is shown with a capital VBE. So just remember that difference. Mostly it's not such a great difference, but in some cases we need to pay attention to that difference. As we do problems, you will understand that better. But just remember that they do come in two different ways. Okay, so I'm going to move on. We have plenty of theory to cover. So, and I know we already finished more than half, about half of it, half the time. All right, so I want to spend a little time on making sure that you understand the actual forward bias, reverse bias business a little better. Okay. Now, in the previous drawing, we kind of showed the base as being common, right, to both this side, the left side, and the right side circuits. But unfortunately, or fortunately, a lot of times the way transistor circuits are shown isn't exactly like what we showed previously, but they are shown more in this way. Okay, so here we have also the emitter, the base, and the collector, so nothing has changed, but we show the emitter grounded, and then the VBE, the external voltage applied to the base, is in this form where there is a battery. The positive of the battery is connected to the P region, the base region, but the negative is also grounded. Similarly, on this side, we have a battery, we call it VCE, and the positive of the battery is connected to the N region because we need reverse biasing, right? So the positive of this battery is connected and the negative goes to ground again. So basically this circuit that you see on page 7 is no different from this circuit, okay? But it can cause confusion in a couple of ways. First, we've brought in the ground connection instead of this common connection. And also here we call it VCB. VBE is the same in both cases, but what we call VCB in this drawing on slide 6, we now bring out VCE in the circuit on page 7. Now I can assure you they are the same thing. It's just a way of naming it that can be a little confusing, but it can't be helped. You have to understand both approaches and be able to relate one to the other. And to help you to understand, remember, I've got some notes here, so let me quickly read those so you understand. Okay, so I've given some values here. The VBE voltage is 0.8 volts and VCE is 1.0 volts. Now we know that this junction has to be positive forward biased, right? So forward biasing, if you know that this is a PN junction, a PN junction needs more than 0.7 volts, 0.7 or slightly greater than 0.7, and then we can safely say yes, it's forward biased. So we've got 0.8, and so the base is 0.8 volts above ground, right? So if in this connection, this 0.8 means that this base P is 0.8 volts above ground. Now, so that means it's forward biased. Now let's look at the collector voltage, right? This voltage. The collector voltage is 1 volt above ground, right? This is 1, because this is 1, the negative, the other terminal of the battery is connected to ground, so we can say collector is 1 volt above ground. So what does that mean? So base is 0.8 volts above, collector is 1 volt above, so you can actually say collector is the difference 0.2 volts above base, right? So VCB equals VCE minus VBE, which is 0.2 volts. So the nice thing is VCB, which is the collector to base voltage, is showing a positive value, that means the collector terminal, which is actually connected to the N region, now is actually connected to the positive of the supply, positive of some supply, right? Let's call it VCB. So it's connected to the positive 0.2 volts of the VCB voltage, and the base of the VCB is hence connected to the negative of that imaginary voltage VCB, right? And because the N region, which is a negative region, is at a positive voltage plus 0.2, we are also meeting that other condition, which is that the junction needs to be reverse biased, right? For this junction to be reverse biased, the N region should get a positive voltage and the P region should get a negative voltage. Then you can say it's reverse biased, which is exactly what we have done by this arrangement. So the collector, because it's plus 0.2, slight positive, right? Not too much, but enough that we can say that the collector base junction is reverse biased by 0.2 volts. So remember, this is how you're going to see a lot of the circuits. So just become comfortable that even though you don't actually see a battery called VCB, we call the batteries VBE and VCE, but you can imagine there is an imaginary battery that exists called VCB, and it's making sure that the N region, the collector region, gets a positive voltage and the P region gets a negative voltage with respect to that junction, right? Even though it is relying on two other batteries to make that happen. Okay, so bottom line, as long as this VCE is slightly higher than this, you are meeting both conditions, that this junction between the emitter and the base is forward biased, while this junction between the base and the collector is reverse biased. Okay. Also, one last thing to note, in the NPN transistor, base and collector voltages are higher than emitter because we have grounded the emitter, right? So both base and collector voltages with respect to that grounded emitter will always be at a higher value. And so the statement that base and collector voltages are higher than emitter voltage. Okay. All right. Let's move on to slide 8. Now, slide 8, I kind of should have waited. In our textbook, he waits a bit to bring you this terminology and this method of drawing a BJT, but I thought I'd bring it to you earlier because you might as well become comfortable with the concept. This is exactly what I just showed you in the previous slide. The emitter region is shown with that little arrow. Okay, that E means emitter, B means base, C means collector. We just drew it like this here, emitter, base, collector. Now we draw it like this, E, base, collector. The emitter is grounded, the base has a battery and the other end of it is grounded. The collector has a battery, the other end of it is grounded. And the same values of the voltages, VCE plus 1, VB plus 0.8, and the same logic, but instead of showing it like this, most problems, most situations, you're going to run into this. So keep both slide 7 and slide 8 handy in your memory so that as you do more advanced work, you can immediately understand why even drawing it like this and with these values of voltages, we can still say that the transistor NPN, a BJT, is in active mode and we are meeting the conditions that the first junction, the emitter base junction, is forward biased and the second junction, base collector junction, is reverse biased. Okay, again emitter connected to ground, base voltage is set to about plus 0.8 volts, the collector voltage to a higher value, that is plus 1 volt, and so the VCB, which is between the collector and the base, which needs to be a reverse bias, and to reverse bias you need to have it positive. We have a positive 0.2 because it's the difference of these two, and then we say that the CBG experiences a reverse bias of 0.2 volts. Okay, so I'll leave it at that. 7 and 8, please spend some time, make sure you understand the logic here. Okay, slide 9. Now we bring in a lot of formulas. Okay, on the right side the drawing is what you saw a couple of slides ago, nothing different there. But now we are trying to say how are all these currents and the voltages related. Okay, so we have IE, IC, IB, the currents you already saw, but a couple of new things also. So let me go down this list of what we are saying here. Now again, the derivation of all this, the physics behind this, how all this comes about, there's plenty of material in the textbook. Please read it so that you get a better understanding, but I certainly will not have time to derive all that, so I'll give you the summaries of the formulas that help us keep moving and to do problems, but if you want to understand a lot of the logic behind this, you'll have to read the textbook. Okay, so the collector current, this is one of the most important things we continuously have to come up with in problems. What is the collector current? The collector current is important and it is related to the base emitter junction voltage. Okay, this relationship is exactly, you're right, it is a diode PN junction relationship, right? We used to call this the I diode, ID, and we used to call this the V diode, VD. Here they're slightly different. We call it I collector current, and the V diode, we call it the V base emitter junction voltage, VBE, but the relationship has the same exponential form, and as long as VCB is greater than 0, that means it's forward biased. This relationship, the diode equation for the current, is now used, and we call this, the left side, we call it the collector current. So that's the first thing that we come up with. Of course, above that is that another relationship, IE equals IC plus IB. So this current is the sum of this current plus this current. Okay, this is a relationship 1 or relationship 0, then relationship 1. Relationship 2 is also a diode look equation, but the IB, instead of just having IS, it's got an IS by beta. Similarly, I emitter, instead of just having that diode relationship IS, we have something called alpha introduced, IS by alpha. Okay, so IB and IE, all three have that diode exponential relationship for the currents, but in this case it's a straightforward copy of the diode relationship. Here we bring in these two factors called alpha and beta. Alpha and beta, they are given by the manufacturer. So if the manufacturer is going to make 1,000,000 transistors, NPN transistors, in one production lot, he will say all my transistors will have roughly this value of alpha or beta. Beta is usually 50 to 200, alpha is usually 0.95, less than 1. Okay, and so beta is more commonly given, and then you derive alpha using this relationship. So the beta of a transistor is usually between 50 to 200. So for a given batch of transistors made from one production line, the manufacturer may say, okay, my beta for my transistor is about 100 plus or minus 20%. So generally there's a wide variation because manufacturing process makes it wide, get that variation. So the manufacturer will give you the alpha, and then we use that alpha in all of the equations. Couple more very important relationships. Now we know the I collector depends on the V base emitter voltage, right? That junction voltage. Vt is the same Vt that we already know, the thermal voltage, which is about 25 millivolts, right, at room temperature. But IC can be thought of, can be shown to be beta times IB. So if you have beta as 100, that means I collector is 100 times I base, right? I collector is 100 times I base. And I collector is also related to I emitter by the alpha factor, and the alpha is always less than 1, never 1, it's always less than. And so I collector is about 0.99, 0.98 of I emitter. So the I emitter value is slightly higher than the I collector value, or I collector slightly less than I emitter. Okay. So these are important relationships. Please become familiar with them. A little more about IS, because the same IS comes here, right? And you may be wondering, okay, we got an IS, and we know IS applies to a diode relationship, but what exactly is IS when it comes to this device? Because now we have two junctions, right? So on slide 10, I give you a lot more detail about what the IS is. It follows the exact same form that you're probably comfortable with. It has these factors: area, diffusivity of a certain region, Q, the charge of the electron, Ni, the intrinsic carrier concentration, Na, accepted doping level, W, width of the base. So much of this refers to the base here. So as you read through this list, you'll understand that we are talking about the parameters within the base, and they define how IS comes out. Okay, IS is still a very low value, 10 to the power minus 16 or something, but how exactly you derive it, you look at all these values for the base and then use it in the formulas. Okay, all right, I'm going to move on to slide 11. Here, this is not from our textbook, but I thought again I bring it in so you become comfortable looking at this way of visualizing the transistor, the NPN. This is the more commonly used. And here, all I wanted to point out is that these voltages VBE, VCB, VCE are shown. And when we talk about them, this is how to imagine them. And this relationship is important. VCB generally is VCE minus VBE. These are external battery voltages, so you can understand what they mean. But VCB is more of an internal voltage, and this is how they are related. So again, the emitter supplies the charge carriers, which are electrons in the case of an NPN transistor, right? The collector collects them, and the base controls the number of carriers that make this journey. So that's one of the simplest ways to understand what's happening within an NPN transistor. Okay, moving to slide 12. This is a busy slide, but I've tried to summarize everything that we have learned so far into one slide. So, important slide, please read it carefully, spend time understanding every one of them, so that as we move forward, you have this base knowledge that is essential. Okay, so quickly reading this: the emitter base emits charge carriers, electrons in case of an NPN. The collector collects them, and the base controls the number of carriers that make this journey through the base emitter voltage VBE. Diffusion is the primary mode of movement of these carriers. You remember diffusion and drift, right? And what we are saying is primarily it's diffusion, even though you have all these voltages applied, right? The voltages that are applied create concentrations of minority carriers. And all this physics you can read in the textbook a little more, but just understand that diffusion is the primary mode of movement. The forward bias voltage VBE determines the current IC in the collector terminal. We saw that relationship already. The collector current IC is independent of the value of the collector voltage as long as the collector base junction reverse bias, that is, as long as remains reverse biased, that is, as long as VCB is greater than or equal to 0, then you can almost say the collector current has nothing to do with the collector voltage, it only depends on the VBE, base emitter voltage. In the active mode, the collector terminal behaves as an ideal constant current source where the value of the current is determined by VBE. Same thing as what we just said above. The emitter collector IE is equal to the sum of the collector and base current. So it's like Ohm's law, KCL, right? I mean, sorry, not Ohm's law, but KCL. We have two branch currents, the collector current and the base current. If you add them, they add up to the source current, which is the emitter current. Because the emitter is actually what provides the electrons to begin the collector current, the currents to begin. Also, IB is much smaller than IC, and IE approximately equals IC. Not exactly equals, remember there's the alpha factor 0.99, 0.98, but in many cases you can visualize that the collector current and the emitter current are roughly equal. IC equals alpha times IE, generally alpha is slightly less than 1. So again, I hope you are able to by now completely become in control of all these ideas in slide 12, because they are all important as we move ahead. Okay, I'm moving ahead to slide 13. Here, for the first time, we talk about models, and we're going to use a lot of models. The textbook certainly likes models. We don't always have to solve problems using models, but models are important. So let's start by understanding what they are. So this equation, the diode equation that now connects the collector current to the base emitter junction voltage, and of course we have the VT and the IS, which are mostly constant. This relationship you can model through the circuit. So what is the circuit? We have independent voltage V1 and we have a dependent current IS, and the I collector, right? This is the I collector, sorry, not IS. So the I collector is the dependent source, and V1 or V input is the independent source. And what is the value of the dependent? It is related in this fashion to the independent voltage source through the exponent, so the V1, and then IS and VT are pretty much constant. Okay, so that's the way you can visualize this relationship, and then we say the transistor operates as a voltage controlled current source. So it's a current source, and that is the collector current. Most cases the collector current depends on the base emitter voltage VBE, but otherwise it operates almost independent of any other factor. Okay, so that's the way to visualize one model. There's more models that the textbook introduces to us. There's the voltage controlled current source, the current controlled current source. Here you'll see this is the same as what we just talked about. This is the voltage controlled current source, right? We already mentioned that in the previous slide, slide 13. So that's just being repeated, slide 14. Then if you convert this collector current into something that relates the emitter current, IE, using alpha, and IE we know also depends on it's also a dependent source, right? IE is also dependent, it's a current, but it's dependent on the base emitter voltage, because we saw those formulas previously. All three of these currents actually depend on VBE, the junction voltage, the forward bias junction voltage. But then they also have the alpha beta connections between themselves, right? So basically all we are doing is reworking with those relationships to create these four models. Generally these two models are used in what's called the common base model or common base connection, while these are used in the common emitter models. Again, you still haven't been introduced to those, so don't get too worried. But just remember that we have the voltage controlled current source appearing twice and the current controlled current source appearing twice. In one case, we use the VBE. In the other case, the current, we use either IB here or IE here, along with the alpha and the beta. Okay. So as we apply these models, you may become more comfortable. Right now, don't worry too much, but I wanted to introduce them to you. Okay. Then on slide 15, we finally come to our very first problem, which I will not do now. We'll wait till we come to the problem section. But basically, what it says is to find the collector current. And to do this, we start by remember the diode equation. That same thing we begin, because we are given VBE and we need to find the collector current. But we will also use these other values. So we'll wait to do that. There's also an example. I'll wait to do that. So let me move ahead with the theory a little bit, and then we'll come back to these problems. So we are on the slide 17. Finally moved ahead to 6.1.3, where we talk about an actual transistor, and this transistor shows you what it actually looks like, right? Actual. You'll see that the end region on the collector is much bigger. The emitter is small, the base is much wider. So they're not all equal to each other, although they seem to be in the previous drawing. So the collector surrounds the emitter region, thus making it difficult for the electrons injected into the thin base to escape. So there's nothing leaking out anywhere. This makes the alpha close to 1 and beta is hence large. The device is not symmetrical, and thus the emitter and collector cannot be interchanged. When we study effects in the next chapter, you'll find that they are symmetrical on the both sides and you can interchange, but with a BJT you cannot. Okay. Moving on to slide 18, where we spend a little more time on saturation, right? So far we've only talked about the active mode, but you have to become equally comfortable with the saturation mode also. We don't talk too much about the third mode, which is called the cutoff mode, but active and saturation are important. So what happens in saturation? So here's the definition. An NPN transistor whose EBJ is forward biased, usually VBE is 0.7 volts, will operate in the active mode as long as the collector voltage does not fall below the base voltage by more than 0.4 volts. That means the collector voltage should not be less than this VBE by more than 0.4. If it falls more than 0.4, then the transistor enters saturation. So this is what you see, right? If the base voltage is taken as a reference, the collector voltage should not fall less than minus 0.4 from the base voltage. This is okay. Although this is not desirable, from 0 to minus 4, we call it soft saturation, but the transistor is still active. But definitely if the collector voltage falls more than minus 0.4, that means if it becomes minus 0.5, minus 0.6, etc., then we say the transistor is entering saturation. Okay. So remember the rule. The collector emitter, let me start again. The emitter base junction has to be forward biased, so that you understand, not a problem. but the base to collector junction has to be reverse biased, right? That means this is positive, this is negative, right? So the negative N, the collector region, should get a positive voltage. Only then is it reverse biased, right? So as long as the negative collector region gets a positive bias, it's happy. We call it the active mode. But once the negative N region starts to get a negative voltage, then it starts to become forward biased, and then that transistor enters saturation. That's why you see, as long as the junction, the base collector junction is positive, that means it's reverse biased, it's happy, it's in the active mode. But once you start to actually give it a negative voltage, we are actually forward biasing that junction, which it doesn't like, which is not suited for our applications. So as you start to give positive voltage, as you start to give negative voltage, it enters saturation, okay? So positive voltage on the VCB, it's happy, negative voltage is happy up to a certain point, but higher than that, it's going to enter saturation, okay? And then once you enter saturation, the currents are modified. You now have some ISC factor introduced, and that kind of starts to mess things up. I know we are running over, but let's see if we can finish this in one sitting so I don't have to come back. So bear with me, please. I'll try to finish in the next 5 to 6 minutes. Okay, so I have a little more detail here to explain the idea of saturation. I think you'll benefit a lot by carefully studying this slide and understanding it, because again I use this model where we have external batteries VBE and VCE, right, instead of this kind of voltages where we have BCB and VBE, right? This is the more realistic. This is how it's actually done in the real world. So we have one battery, the forward bias battery on the NPN side, that is always fixed, generally 0.7, maybe 0.8. So assume that's fixed. Then we have this battery. That determines whether you are in active mode or in saturation. So let's go one at a time. And remember this relationship. This junction voltage, VC to B, right, collector to base, is actually VCE minus VBC. Okay, so when VBE is 0.7 and VC is plus 1 volt, so C, this collector, is more positive than B, right? Because remember, B is at 0.7 and this is at 1. So VC, the collector, is more positive by 0.3 volts. So compared to the base, it's plus 0.3. So as long as this is positive, it's reverse biased. So CBJ is reverse biased by 0.3 volts, and we say we are in active mode. Next, VB is 0.7, but VCB is dropped to 0.4. We've reduced it to 0.4. Is it still active? Let's see. C is less positive than B by 0.3 volts, right? Because this is 0.4, this is 0.7. So C is less positive, so VCB is minus 0.3. Now, CBG has become forward biased. It's not reverse biased anymore by 0.3 volts, but we are still in active mode. So we are in the soft saturation mode, right? We are still active, but not a healthy mode. The transistor is still active, but it's kind of in saturation. Let's look at the last line. This is 0.7. The VCE has fallen to 0.2. It's decreasing, right? It may soon go into the negative, but it's still positive, and so C is less positive by 0.5. That means VCB is minus 0.5, right? Now CBJ is fully forward biased by 0.5 volts, and we have definitely entered saturation mode. Okay, so to summarize, VCE of an NPN transistor is greater than 0.3. That means VCB of an NPN transistor has to be greater than minus 0.4. So greater than minus 0.4 VCB, it's happy, it's reverse biased, and it is in active mode. It's not greater than 0, but greater than minus 0.4. Once VCB becomes in the opposite direction, it becomes minus 0.5, minus 0.6, minus 0.7. That means VCE is becoming more and more negative, which is forward biasing, right? The more negative it becomes, the N region gets the negative voltage, the B region gets the positive voltage. That junction is becoming forward biased more and more. We're actually entering saturation. So I hope these inverse relationships are something you are able to follow and understand, because this is crucial to appreciating all the inner workings of the BJT. Okay, let me take 4 more minutes and finish this, or at least stop after 4, and then we'll resume the remaining later as time permits. Here we talk about the PNP transistor for the very first time. Like I told you, PNP, everything is opposite. Now, instead of the electrons being the primary way of conducting, of finding currents, in the transistor we have holes that are taking the lead role. So holes are emitted by the emitter, the P charged emitter, and collected by the P charged collector, right? And then the base is N in this case. The voltage, the forward bias still applies, the reverse bias still applies for active mode, and forward bias of a PN junction means the P is positive, the N is negative, the N region is negative. A reverse bias on this junction means the P region, the collector region, gets a negative voltage and the base region gets a positive voltage. Okay? In active mode, we say that the VBC, previously we used to talk about VCB, right? But here we say the VBC of a PN transistor has to be higher than 0.4 volts. There are models, there are circuits. Here's a summary of all the modes and all the relationships that we have looked at so far. The 3 currents, how the currents are related to each other, the alpha and the beta, and how they are related to each other, the VT, the thermal voltage. It's all been nicely summarized. A couple more important relationships for problem solving that you'll see in the next few slides. I also brought them here so you have everything in here. And also, what is an active mode? VCE of a NPN transistor has to be greater than 0.3. For a PNP transistor, it's the VEC has to be greater than 0.3, assuming that the other junction is at 0.7 volts forward bias. Okay. All right, we have some problems, and I think I'll stop here and we'll do this section when we come back, 6.2. Okay. So I'm slightly behind, but can't help it. We'll record again. Okay. Thank you.